Hello, welcome back, everybody. Today we're going to be doing section 10.3, which is all about polar coordinates. This is kind of a fun section because I get to introduce you to a brand new coordinate system. And it's kind of a fun and rewarding coordinate system because it lets you describe certain things a lot easier than before. So let me pull up the slides and let's get started. Here we go. Let me set one more thing. Oh, there's also a bunch of pretty pictures in this one as well, so that's another nice thing. There we go. Okay, so let's take a look at the overview. So first, we're just going to talk about and kind of review what a coordinate system even is. What's the definition of a coordinate system? Then we're going to review the Cartesian coordinate system, which you are all very familiar with. That's the coordinate system you've been using since you were first introduced to a coordinate system. Then we're going to develop the polar coordinate system, which is what this section is all about. We'll talk about how to convert between the two coordinate systems. Then we'll discuss polar curves, and that's where all the pretty pictures start to come in. Polar curves, symmetry in this new coordinate system, and then how to sketch polar curves. So one thing I'll say off the bat is that this section takes a little bit of time. So sketching polar curves is really what the majority of the section is going to be spent on, because you need to be able to sketch these curves comfortably and in a meaningful way that you can make sense of. Most of this stuff is just kind of a setup and developing the system itself. But then this is the primary skill that we want to take away from this section, is how to sketch these kinds of curves. There's also a really nice Desmos demonstration at the end, so you can always use that as well, just to kind of like explore. I'll show you when we get to that point. All right, but let's start with coordinate systems. So what is a coordinate system to begin with? A coordinate system is a system that uses one or more numbers or coordinates to uniquely determine the position of points or other geometric elements on a manifold such as Euclidean space. So put more succinctly, a coordinate system just uses some numbers that basically allow you to locate a point in space. This is just a more general concept of a coordinate system because you can generalize a lot of what we're learning. But for our purposes, you can basically think about it as a pair of numbers that tell you exactly where a point is on the plane. That's the basic idea. So that's a coordinate system. You've only been using one coordinate system for probably your entire math education, and it's called the Cartesian coordinate system or the rectangular coordinate system. And it's called the rectangular coordinate system because your coordinates have a rectangular relationship. So when you think about the x and y, the xy plane, x and y are perpendicular in the sense that they form an orthogonal relationship. So they're like right angles. They're at right angles to each other. So rectangular. Also, the box that's formed when you want to locate a point is a rectangle using this system. So there are actually infinitely many coordinate systems. So we're not just restricted to these two. There are infinitely many that you can use. Some are easier to use than others, depending on the context. And that's one of the benefits of learning these different coordinate systems, because oftentimes a behavior or a phenomenon will be described better in a certain coordinate system and not as well in another coordinate system. And we've seen that before, actually. We've seen that before with like the cycloid, for example, that it's much easier to describe that particular curve in a completely different way using a different set of parametric equations, right? So we're going to do something similar to that. So in this section, we're going to learn about a new system called the polar coordinate system. And then when you get to Calc 3, you're going to learn two other coordinate systems, the cylindrical coordinate system and the spherical coordinate system. And these are all actually related to the polar coordinate system as well. The cylindrical coordinate system is basically the polar coordinate system with a third dimension attached. So a height dimension attached, you could say. All right, so let's go back and review the Cartesian coordinate system. So for the Cartesian coordinate system, we use these ordered pairs, x comma y, and that uniquely determines the location of a point in the plane. The plane we denote by R2, which is just r cross r. So you can think of the x-axis as a real line and the y-axis as another real line, and we're crossing them orthogonally, perpendicularly. The values x and y are the horizontal and the vertical displacement of a point. So this distance right here gives you the vertical displacement of this point from the origin. or from the x-axis, I guess I'll say, and then this distance here, or that number there, gives you the displacement from the y-axis. The axes meet at a point called the origin. That's the point 0, comma 0. And the location of any point on this plane can be described in this way. So basically, if you give me any point, say this point right here, this point right here, then we can find the horizontal and vertical displacement and tell you exactly where that point is in this system. So that's the basic idea. Now, for the polar coordinate system, things are a little bit different. So we are still going to describe two-dimensional space. So we're still going to be describing R2. So all of our attention is still focused on the plane, except now it's not going to be the XY plane anymore because we're not going to use X and Y to describe points. We're going to use R and theta. So in the polar coordinate system, our ordered pair is actually R and theta. And this uniquely determines any point in the plane. And here's how we set it all up. So the first thing we're going to do is we're going to fix a point called the pole, or the origin. So there's still an origin here. And we're going to let theta be the angle between a ray that originates at the origin and is parallel, or should say coincides with the standard x-axis. And theta is the angle that you get when you tip up this ray from the x-axis. This is actually what we call the polar axis in this case, and we like to coincide the polar axis with the standard x-axis. All right, so this is the angle theta, and the number r is basically the radius of the circle centered at this point that has this line as its radius. So you can think about it like so. That's basically it. So one way you could imagine this is take the xy plane. Let me actually grab a pen here. Take the xy plane, like so, and center our pole right at the origin there. What we're trying to say is that we can identify the location of this point right here using either x and y, or we can use the coordinates r and theta. And what's r? R is basically let me change the color here. Yeah, I'll stick with it. R is basically the radius of the circle that contains that point. There you go. There's the radius r. And theta is the angle that you tip up to get to that point. So the way that I like to think about it is you basically tip up at this angle theta, and then you shoot out by this distance r. And then when you do that, it'll give you the location of that point. And that is the point that we call r comma theta. Oop, that's a comma right there. I know that looks a little bit like a 1, but that's a comma. Boop, there we go, r comma theta. And that's the basic setup, all right? So these are things I already said, actually. So the ray representing the polar axis typically coincides with the positive x-axis. Just like before, if theta is positive, that means you're going to be turning counterclockwise. Oh, it's always hard to do backward. Is that right? Wait, I think so. I can't tell. And then, oh yeah, and then this point r comma theta gives you the coordinates of this point right here. And again, this works for any point in the plane. So if you give me any point anywhere in R2, then I can find that. So let me actually pick a point right here. If you give me this point right here, then what we can do is we can draw a line, a ray that goes right to that point and has radius r. And then there's an angle associated with it, theta. And then this is the point r comma theta. That's the idea. And that works for any point. All right, now here's where things get a little bit funky, but it's not too bad once you get the hang of it. We can actually extend the meaning of our coordinates r comma theta to include negative radii. So in other words, what does it mean when you talk about negative r? And we can make sense of this, and we can include this interpretation in this new coordinate system. When we talk about a negative radius, what we mean is that the ray that you would normally have is reflected through the origin. So in other words, it's basically rotated 180 degrees or pi radians from the original point. The reason that I like to think about it as a reflection is because if this is like your positive radius, then the negative radius would be the same length, but in literally the opposite direction through the origin. So it's like a perfect reflection. That's the idea. So that's what a negative radius is, and we're going to play around with this in just a minute here. The other thing is this, each point in the plane has infinitely many equivalent representations in this polar coordinate system. And the way that you can achieve that is basically by adding 2 pi to each angle. And every time you add 2 pi, that's a full rotation of the circle. So for example, this point right here, r comma theta, is equal to the point r comma theta plus 2 pi. So r comma theta is equal to r comma theta plus 2 pi, because that just involves going all the way around the circle once and ending up back where you started. So there are infinitely many representations of these points. You can also use negative radii to your advantage. So you could take a point over here and then reflect the radius so that you actually got this point over here. And we're going to see that in a minute too. This idea of having infinitely many representations might seem a little bit weird, or you might feel like it's unusual, but I want to assure you that it's actually not unusual at all, and that even with the Cartesian coordinate system, every point has infinitely many representations. The easiest example is just to think of equivalent fractions. So let me give you this example up here. Let's say I'm in the Cartesian coordinate system. Oops. And I've got the points, let's say 2, 8. Well, I can write that point as 4 divided by 2, and maybe we'll say 2 cubed. There we go. There's another perfectly valid representation of the point 2, 8. And so it turns out that every point in the Cartesian coordinate system also has infinitely many representations. So this isn't too weird of an idea. Okay, now let's practice a little bit. So let's plot the following points given in polar coordinates. And before we do this, I want you to kind of practice it on your own, and then I'll give you a little bit of a tip before you get started. For one, just remember that this is the radius and this is the angle. So these are ordered pairs, and they're ordered pairs given by a radius and an angle. So when you try to plot these on your own in a minute here, just remember that the first coordinate tells you how far out to go from the pole, and the second coordinate tells you how far to tip from that polar axis. All right? Okay, so let me throw up the thinker for just a minute here so you can ponder how you're going to do this. All right, now remember, you got to say something out loud. It doesn't matter if it's to yourself or to your dog or to your infant or brother or sister or whatever. Just say something out loud. All right, now you try to do it yourself. Try to plot these points that are given in polar coordinates. So draw yourself a little horizontal ray, and then think about what angle you would have when you tipped up from that ray. Go for it. All right, now let's take a look together. I actually have these nicely plotted, so I'm going to use the slides to my advantage here. This is the point 1 comma 5 pi over 4. And so what I'm going to do is kind of emphasize some things. If you look at this figure, this is the polar plane. And what I have plotted, or I'm sorry, at least what I have marked on here, are all of the standard angles. So pi over 3, pi over 4, pi over 6, pi over 2, and then all the others, right, going around and around. Then I have a bunch of concentric circles. So these concentric circles are circles of radius 1, 2, and then beyond. So how do we plot this point? Well, it should be lying on a circle of radius 1. That's why it's on this circle right here. And it should be at an angle 5 pi over 4 from the polar axis. So the polar axis is right here, shooting off like that. So we need to go an angle of 5 pi over 4 from that. And these are just the standard angles that you remember from, or like the standard representation that you remember from trigonometry or pre-calculus or something like that. You just go around 5 pi over 4 radians, and then you're going to go out to this point right here. And that's the point 1 comma 5 pi over 4. Not too bad, right? Not too bad. Here's the point 2 comma 3 pi. So here we're out on the circle of radius 2 now, because our radius is 2. And then we're 3 pi radians around, so that means we're going to go around a full rotation and then stop right there. And then the point is going to be right out here. So maybe if I erase this for a minute, just to emphasize, the length of this line here is 2. Oop, what am I saying? That's r. The length of that line is 2, and the angle that we traveled to get there is 3 pi. Right, here's 2, negative 2 pi over 3. So again, our radius is 2, so we're on a circle of radius 2. Now the angle is negative, so that means we went clockwise from the polar axis. So in this case, we went this way to get to that point. Negative 2 pi over 3 is the angle, and the radius is 2. Oh, that's so funny that I keep doing that, 2. All right. Okay, now here's one where I was trying to be a little bit tricky. So remember that these are ordered pairs. They're ordered pairs. So this is r, and this is theta, the angle. You can represent angles in radians, or you can represent them in degrees. That doesn't matter. They're both angle measurements, right? So if we're talking specifically about an angle, we can represent it using degrees or radians. In this case, I use degrees, and my radius just happens to be the number pi. So the fact that it's the number pi doesn't change anything. That's just the radius. The radius happens to be about 3.14 here, pi. So you go out exactly pi units from the pole, and the angle that we swept out was negative 15, oops, bring that back, negative 15 degrees. And there you go. That's the point, pi, comma, negative 15 degrees. All right, next, okay. 1/2 comma 4 pi over 3, just to kind of point out again, like the radius can be any real number. It could be any positive real number. It could be a negative real number. We're going to see more of that in just a minute, but the radius can be any real number, and even the angle. The angle can also be any real number. In this case, it's 1/2 comma 4 pi over 3, so we're on the circle of radius 1/2. Maybe I'll zoom in a bit. There we go. We're on the circle of radius 1/2. And the angle that we had to sweep out was 4 pi over 3. So let me do this. There's our 1/2, and we went 4 pi over 3 to get to this point. 1/2 4 pi over 3. All right, not too shabby. Let's do one more, e comma 2. Here's another one where I was trying to be a little bit tricky. E is the radius, so this length right here is e, and the angle is 2. Now there's no degrees listed here, so this is to be taken as radians. So this is 2 radians. So the angle swept out from here to here is 2 radians. And that's the point in polar coordinates. Okay, now let's do this. So let's consider the point 2 comma pi over 3. And what I want you to try on your own here, and then we'll do it together, is to find 2 other equivalent representations of this point in polar coordinates. And just to make it a little bit more edifying, I want you to come up with an equivalent representation where the radius is still positive, and I want you to come up with one where the radius is negative. All right, and just remember, when you have a negative radius, that's basically a reflection through the origin. So let me throw up the thinker for a minute here. Think about how you're going to approach this. All right, now say something out loud about how you're going to approach it. Maybe what would you try first? What would be your first attempt at an equivalent point? All right, now try to work it out on your own. Find 2 other representations, and then we'll do it together in just a moment. All right, here we go. So I've got these written out, so I'm going to rely on the slides. Actually, it looks like I did 2 representations for each case, so we'll just look at both of them. So first of all, consider the point 2 comma pi over 3 and where it is on the polar plane. So you could even do this kind of thing on your own. You could say, okay, where's 2 pi over, or where's 2? In fact, it's getting a little bit too messy. Let me do this. Actually, you know what? I kind of like this. This is 2. Pi over 3 is right here. So this is the point 2 comma pi over 3. There we go. That helped me organize my thoughts a little bit. All right, so that's the point 2 pi over 3. An equivalent representation would be that point plus 2 pi. So another one would be 2 comma pi over 3 plus 2 pi. But that's exactly what this is right here. That's pi over 3 plus 2 pi, since 2 pi is 6 pi over 3. So you could say this point is also equal to 2 comma 7 pi over 3. And then you could do it again. So that's what I did for this point right here. What I did was instead of adding 2 pi, I added two pi's. I added 4 pi, and that's what gives me this other point right here, like so. So there's two equivalent representations with positive radius. Now let's look at the other case. Let's look at the case where the radius is negative. So if the radius is negative, we're going to negate 2. So the radius in this case has got to be negative 2. And what that means is that any line that we're imagining is going to be reflected through the origin right here, or through the pole. And so that's why my angle has to accommodate that reflection. So let me point this out right here. And what I'm going to do is erase this. And I'm going to go around 4 pi over 3 radians. I'm going to use a different color here. So if I go around 4 pi over 3, that's right here. So this blue angle is 4 pi over 3 radians. But if I considered the point 2 comma 4 pi over 3, that would be right here. That would be the point at the end there. But that's not the point that I want to describe. I want to describe the point that's exactly opposite that point right over here. So what I do is I negate the radius. And what that has the effect of doing, is literally reflecting this line through the origin so that it goes this way. And then we have an equivalent representation. So this is the same as negative 2, 4 pi over 3. Just like that. So there's another one. And now here's another representation. So look at the next piece down here. What I did was the radius is still negative 2, but now rather than have a positive angle, I decided to use a negative angle in this case. But you're going to see that you get exactly the same thing. So check this out. Negative 2 pi over 3, that's the same as going this way, 2 pi over 3 radians. So that would land us right here. So this angle right here is negative 2 pi over 3. Then the negative radius is going to reflect through the origin. So you'll get this point right here. And so equivalently, we have negative 2 pi over 3. So there's all sorts of clever ways of rewriting the same point. There's 4 different ways of rewriting the same point. So keep those different representations in mind when you do this kind of stuff. And depending on the context, you can kind of choose whichever representation is easier for you. A lot of times just the basic representation is easiest, but you never know. Sometimes it's handy to want to reflect a radius, and we're going to have to be comfortable with that concept of reflecting a radius. Okay, now that we've kind of seen this system, let's talk about how to convert between these two systems. And we're going to get a fancy word here to describe this. So what is an isomorphism? Let me get my laser pointer here, an isomorphism. So an isomorphism is a structure-preserving mapping between two structures of the same type that can be reversed by an inverse mapping. So this is the takeaway. This is why we need to know this word. The Cartesian coordinate system and the polar coordinate system are isomorphic. So what this means is that you can describe any point in the plane with either one of these systems. And you can convert between these two systems through a set of what are called isomorphism equations. What are isomorphism equations? Literally equations that relate the two structures. And we're going to see those right now. You actually already know these. So if you took pre-calculus or you took trigonometry, you've been looking at these isomorphism equations for a while now. So let me refresh your memory about what they are. Here they are. So these are the isomorphism equations to convert from polar to Cartesian. And these are the isomorphism equations to convert from Cartesian to polar. So you can go back and forth. This collection of equations, those are the isomorphism equations. And this is a picture that I'm sure many of you are very, very familiar with. It's kind of how you define sine and cosine, right? So if the radius was equal to 1, then we would always say x is, oops, I got it backwards, x is cosine theta and y is sine theta. And then if you have a circle of radius r, it generalizes to be r cos theta and r sine theta, which is exactly what this says right here. So those are the equations you use if you want to convert from polar to Cartesian. You just plug in what you know about the radius and the angle, and it'll tell you the x and y coordinates. Now, what if you want to go the other way? What if you've got an equation written in Cartesian form and you want to write it in polar form? That's where these equations come in handy. So let me explain these ones individually. So first, this is basically the Pythagorean theorem. So if you know x and y, you can find out what r is through the Pythagorean theorem. So in other words, if you know this displacement and you know this displacement, then you can find what this is. Now, how do you get the angle? So the angle can be gleaned by using the fact that tangent of that angle is y over x, as long as x is not 0. As long as x is not 0. So, for example, this angle right here, if you wanted to know what that angle is, well, you know what the ratio y over x will be. So then you can basically use arctangent to find what theta is. Now, I don't think I say it explicitly. Maybe I'll add this some other time. There is a little bit of ambiguity here. So one thing I want to point out here is that this equation does not give you, it doesn't give you a single result for r. So maybe as I was saying this, some of you were thinking like, well, wait a minute, if I know x and y, I can get r squared, but how do I know what r is? Because r could be positive or negative. So this is one thing I want to remind you all again. Whenever you take a square root, you have to include a plus minus. This case is no different. So when you plug in x and y and you get a result for r squared, and then you take that square root, you're going to get a positive and a negative result. And you have to choose which one of those results is correct. And this is where that ability to describe a point infinitely many ways comes into play, because you're going to choose if the radius is positive or negative. And remember, there are infinitely many angles that have this tangent value, y over x. So you have to pick the correct angle, and you have to pick the correct value of r. And there are many ways for you to pick. You just have to think about the point that you were trying to describe and ask yourself which representation you want to use. All right. I can explain more during the activity session if you have questions, but let's do some examples and see. Let's do some examples and see. All right, so let's convert this to Cartesian coordinates. This one I want you to try on your own. And I'll just throw up the writer right away. So try this. Convert this to Cartesian coordinates using the isomorphism equations. All right, now let's do it together. This one's not so bad. We know r and we know theta. So we literally just plug in those results to our isomorphism equations. Here's r, here's theta. Cosine of pi over 6 is root 3 over 2. So when we simplify, we get this. Same thing with y. Plug in r, plug in theta. Sine of pi over 6 is 1/2. Simplifying gives us 3/2. And so that means that this point, written in polar form, is equal to this point, written in Cartesian form. Those 2 points are the same point, they're equal. Okay, now I want you to try to do this one on your own, and this one is where that infinitely many representations thing is going to come into play. So I want you to think about this one for a minute on your own. All right, and now say something out loud about how you would start. You just got to say anything out loud about how you would start, maybe what you would use to begin. All right, now I want you to try to work it out on your own. And one thing I will say is that you will have to make a choice about angle and radius. So think about that as you work it out, and then we'll do it together in a moment. All right, now let's do it together. I've got it written on the slides here. So first, we can use this isomorphism equation to get the radius. So we plug in x and y, simplify, and then solve for r, and we get these two choices. So r is plus or minus 2 root 2. And let's just hold on to that for a minute. Now, let's find what theta is. So when we plug in y and x to our equation for tangent theta, we get -1. And so that means we have some options. So already we have lots of options. We have these two and we have these two. So we get to choose the radius and we get to choose the angle. By the way, there are infinitely many more angles that would work for this, but I just picked a couple easy ones. Easy ones that are given in the, or not even the ones that are given in the domain of the, anyway, here are just two easy ones. So you could pick negative pi over 4, or you could pick 3 pi over 4. Both of those rays will give you a slope of -1. Now, we know that the point -2, 2 lies in quadrant 2. So this is where you have to think about where your point actually lies. It lies up here. And so we have to pick the corresponding radius and angle to get to that point. So there's two different representations that I give here. This first one is me picking the positive radius and the angle 3 pi over 4. So what that looks like on my picture is I'm going to go this way 3 pi over 4, and then I'm going to go out +2. Oh, I'm sorry, +2 root 2. And that's this angle right here. I'm sorry, that's that description right there. Now, the other one, what I did was I went the other way. So let me erase these bits. So rather than going an angle 3 pi over 4, I went down to negative pi over 4. But then I picked a negative radius. So I picked r to be -2 root 2. And so that means that this length right here would be 2 root 2, but I'm going to reflect through the origin. And when I reflect through the origin, I'm going to go, well, I'm going to go this way, -2 root 2. And that's that point right there. Or, I mean, that's that representation right there. So you get some flexibility. You get to play with that kind of stuff. Okay, we'll do more examples in the activity, but now let's talk about polar curves. So this is where things get really fun, and this is where the pretty pictures start to show up. So if you've got an equation and the variables are given to you in polar coordinates, we call it a polar equation. If we consider the function r equals f of theta, given in terms of polar coordinates, then what this does is it lets us define a radius given some angle that's been swept out. So in particular, r is a function of theta. So if you give me an angle theta, at that angle theta, I can say how far out you need to go from the origin, plus or minus, right? Because it could be the displacement from the origin. So this is really, really nice because a lot of times you want to describe how far away something is given where it's swept out from a polar axis. Yeah, so it's astoundingly helpful when you're investigating anything that has radial or rotational behavior because it encodes precisely how far to go out from the origin at any given angle. So this is a brand new way of describing anything that you want to describe that has any kind of radial behavior. You can do it almost all the time more succinctly with polar coordinates, right? The graph of a polar equation is the solution set of that equation. It's basically the curve that represents that equation, and it's called a polar curve. A polar curve. And now we're going to see how to make these things. All right. Oh, wait, let me look ahead real quick. Yes. Okay. We're not going to start sketching them just yet. Not just yet. We're going to work and play with the equations for just a minute. So let's start with this. Let's say we have this equation right here, and it's given to us in terms of x's and y's, which means it's a Cartesian equation. How would you express it as a polar equation? Think about that for a minute and see how you would get that to be in terms of r's and thetas. Okay, luckily this one isn't so bad, right? Because we know x and we know y, so we can just plug in r cosine theta and r sine theta and see what we get. All right. Oh yeah, I'll mention this part in just a second here. But here's the substitution. So I replaced x with r cosine theta, and I replaced y with r sine theta. Then you get this equation here, and then I basically solved for r. So I solved for r, divided both sides by cosine squared, and then we get this. So this is a representation of this parabola. I was going to say on the previous slide that this is actually the equation of a parabola. So if you remember from the conic sections part of pre-calculus, this is basically the factored form of a parabola. I can't even say it's the factored form. I almost will just say it's the conical form of a parabola. But this Cartesian equation is just really this Cartesian equation, and this is representing a good old parabola. It's y equals x squared, but squished a little bit by a factor of 1/4. That's all it really is. So you can describe that parabola using this Cartesian representation, or you can describe it using this polar representation, but it's the same object. So check this out. Here's a picture. This is a picture of it. So what I'm saying is that this thing right here, oops, let me grab this. There you go. This thing right here is this written in Cartesian form, but it's also this, oops, written in polar form. Two different representations of the same object. Which one do you want to use? Totally depends on the context and what you're working with. All right, how about this one? Let's convert this to its rectangular form. This one I'm going to do on my own because it does require a little bit of cleverness to begin with. But here's what we're going to do. We're just going to rewrite secant in terms of cosine theta. So remember that this is equal to 4 over cosine theta. So if you multiply both sides by cosine theta, you'll get r cosine theta equals 4. But r cosine theta is just x. So this equation right here is just describing the line x equals 4. That's it. Here's a picture of it. Here's a picture of it. So you can describe it as x equals 4, or you can describe it as r equals, oh, I forgot what it was, 4 secant theta. 4 secant theta. 4 secant theta. Another interesting result here, it's good to kind of ponder how these things work and wonder like why the representations look the way they do. So let's think about 4 secant theta for just a moment. I'm assuming that it makes sense why the line looks like x equals 4. That's just the basic polar representation of a vertical line. I'm sorry, Cartesian representation of a vertical line. But think about 4 secant theta for a minute. Why is it that 4 secant theta describes this line? And one thing I'll point out is, remember that secant is 1 over cosine. So secant actually has some asymptotes, right? And secant blows up to infinity when you approach those asymptotes. And those asymptotes occur at pi over 2 and negative pi over 2, right? So basically, as your angle sweeps out to pi over 2, what's happening is that this equation here is giving you the distance that you need to go out. Right? I can't even draw it well. I'm starting to like curve, but I shouldn't be curving. It should be this straight line straight up like that. So as theta goes to pi over 2, this is describing exactly how much farther you need to go. Secant theta is growing in size, and that's why this radius, the radius, which is all these numbers right here, those distances, the radius is growing really, really large as well. That's why it's describing it. Similarly, if you go backward, you have this same behavior, just like this. So those like radiating lines, that's what 4 secant theta is describing. Or you can just write this as x equals 4. It just depends on what you want to use it for, right? Okay. All right, so this one, is this the tricky one? Okay, this one I want you to try on your own. So think about how you would write this in terms of x's and y's. Think about it for just a minute. All right, now say something about how you would do it. What would you do to try to convert it? All right, now I want you to try to work it out. See if you can get it in terms of x's and y's only. So your final answer cannot have r's or thetas in it. Okay, now let's do it together. This one requires a little bit of cleverness because you might think that a good start is to square both sides. But in this case, actually, you know what? If you square both sides, it might actually work. But I feel like if you square both sides, you're going to be stuck with values of sine that don't have an r attached to them. And you need that additional r attached to be able to convert it into y, right? Because y is r sine theta. So here's the trick. What you're going to do instead is multiply each side by r. So rather than squaring both sides, you multiply both sides by r. Then you get this and this. Now you have the Cartesian equation. And technically you could stop there. Technically you could stop right there. So let me just back up a minute. Oop. This is a Cartesian representation of this equation because there's no more r's and there's no more thetas, and we're now in terms of x's and y's only. But what I have for the rest of the calculation is essentially completing the square and massaging this equation a little bit so that it reveals its structure and we can really see what it is. So I moved everything to one side, and then I completed the square on the y terms, and then in the end we get this. And that, my friends, is the equation of a circle centered at 0, 1 with radius 1. So what I'm saying here, actually I'll leave these two. What I'm saying here is if you want to describe a circle of radius 1 centered at the point 0, 1, you can describe it in either of these two ways. Either of these two ways, it's the same object. It's the same object. Here it is. Here's the point 0, 1. Oops. 0, 1. Here's the radius. The radius is 1. And so you have these two choices. You can represent that circle like so, or you can represent it like so. Either way works. Just depends on which you prefer, which is easier for your application. In some senses, I think this is actually a lot simpler. There's only one factor. There's no squared terms. It's just, I shouldn't say I'm sorry, there's only one term. There's no squared terms. It's not so bad. All right. How about the polar curve r equals 2? So now that we've seen that it's a little bit easier to describe some things in terms of polar versus Cartesian, and it's sometimes easier to describe something in Cartesian versus polar, let's look at some curves that are easy to describe in polar coordinates. So I want you to try this one on your own and try to sketch it right out. So see if you can sketch this curve r equals 2. What's the curve look like? Go for it. Okay, this one's a fun one because if you look at the equation, all it's saying is that the radius is 2. That's it. It's not identifying or specifying anything about the angle. So the angle is a, quote, free variable, right? The angle can be anything you want. All that matters is that the radius is 2. So very succinctly, this describes a circle of radius 2. That's how you describe a circle of radius 2 in polar coordinates. Just r equals 2. Compare that to a Cartesian form, which would be this. 4, there we go. That's a circle of radius 2 written in Cartesian form. Same thing. Pretty cool, huh? All right, how about this one? So this one I want you to try again too. So think about it for a minute and then try to sketch it. All right, I hope your sketch looks like mine. What I see here is basically that the angle is pi over 3. That's all it says. Theta has to be pi over 3. No specification about a radius whatsoever. So in this case, r is the free variable. So the radius of the circle that we're on can be any radius you want. That doesn't matter. All that matters is that the angle is pi over 3, and so this describes this line. This line where the angle is pi over 3. That's what this equation describes. That's what that equation describes. You could also write it in Cartesian form. It's just the equation of a line. You just need to know what the slope is. right? And I'm sure you can find out the slope of this line because, slope is just tangent. So see if you want to, you try that one on your own. Here, I'll throw the writer up again. Try to write it in Cartesian form on your own. Cartesian form. Y equals, there you go. All right. So you practice that, and then I'm going to move on. All right, so let's talk briefly about symmetry. So just like in the Cartesian system, there's symmetry. You can talk about symmetry about the x-axis, the y-axis, symmetry about the origin, for example, that kind of symmetry. So you do have other types of symmetry within the polar coordinate system. So here's one of them. If your equation is unchanged when you replace theta by its negative, by negative theta, then you have symmetry about the polar axis or the x-axis, right? So here's the polar axis. What this is saying is that if your curve has the same result, or if the equation gives you the same result if you go this way or this way, that means you're symmetric about the polar axis, right? This is the description of symmetry through the origin or through the pole. So if you end up with the same shape, or sorry, I should say if you end up with the same results when you replace r by negative r, or when theta is replaced by theta plus pi, this is the reflection through the origin, then, excuse me, then your curve will be symmetric about the pole. So that's possible as well. Notice that these are equivalent conditions. Replacing r by negative r is the same as replacing theta by theta plus pi. That's it. And then lastly, we've got symmetry about the line theta equals pi over 2. So if your equation is unchanged when you replace theta by pi minus theta, then you've got symmetry about the line pi over 2, or the y-axis, if you want to think of it like that. You'll have like a vertical symmetry. All right. Okay, so one other comment I'll make about symmetry before I move on to sketching the polar curves is that, how do I say this? No, okay, I won't wait. So when we start doing integration in terms of polar coordinates, which is going to be the next section, you still want to think about symmetry. So if you remember from Calc 1, if you integrate an odd function or an even function over a symmetric interval, then it can simplify the integration process. The same kind of thing can happen here. And we'll see it a few times in our calculations that if you recognize the symmetry of the curve, then you can cut your calculations in half or cut it to 0. Just wanted to mention it though. That's one of the reasons it's good to consider symmetry. It's not just like a fun one-off. Okay, so next we're going to get into this. And here's where I'll say you may want to go ahead and take a break since this is a bit of a long lecture. We're nearly done, but the last part of this lecture is where a lot of the meat of the topic comes in, or a lot of meat of the section comes in. So go ahead and take a break. You know what I need? I need to throw up like a "we'll be right back" slide. Maybe I'll make that for next time. But take a break, and I'll see you in a minute. I need some like elevator music to play during the break. All right. Okay, we're back. So hopefully that was a long enough break. Now we're going to figure out, or we're going to learn how to sketch these kinds of curves. So here's an example of a polar equation, r equals 1 plus sine theta. And the question is simply, what does this curve look like? So here's the technique, and this is actually very fun once you get the hang of it. This is a function of theta. And so what this is really doing is it's saying r of theta equals 1 plus sine theta. So this function is telling us the distance from the origin at any given angle theta. That's what this thing is saying. It's saying, hey, when you're at theta equals pi over 2, go this far out. And when you're at pi over 3, go this far out. And when you're at pi over 4, go this far out. And it's just saying how far out to go at each angle. So how do we graph what the polar curve actually looks like? Well, it's really, really handy to first graph it in a Cartesian form. So look at the axis labels, the axis labels. Oop, I want to keep that for this Cartesian graph down here. So here's r and here's theta. So what we're going to do is we're going to take this equation and just write it in a rectangular form, and then we're going to use the resulting graph to inform how to draw our polar graph. So all I did here was I literally graphed the function 1 plus sine theta. And you had to do this a whole bunch in trigonometry. This is why you had to do it. This is why hopefully your instructor emphasized it, because now you have to be able to graph these trig functions with, relative ease. So this is the graph of 1 plus sine theta. And what we're going to do now is look at this graph and draw the polar curve. And here's how we're going to do it. Remember that this is the radius axis. So these lines, these green arrows, are telling us exactly how far to go out at each angle. So at this angle, go this far away from the pole. At this angle, go this far away from the pole. At this angle, go this far away from the pole. At this angle, go this far away from the pole. And it just keeps telling us. So some things to notice. Notice that we're going to be going out increasingly far until about here, or until exactly there. Then we're going to be going not as far out. Not as far out. And then when we're at 3 pi over 2, our radius is actually equal to 0. So there's a point where we don't go anywhere. We're just on the pole. Then we keep going out again. So pictorially, this is what it's going to kind of look like. This is what it's going to kind of look like. So these green arrows that you see here correspond precisely to the green arrows that you see here. They are the same length. The only difference is that here they're graphed rectangularly, and here they're graphed in polar form. And that's what you do. So let me put all the pictures together, and I'm going to zoom in on these pieces. So now what I'm saying is all these green arrows correspond identically to these green arrows that you see over here. That's all it is. So once you graph this, you can read that graph and figure out what your graph is going to look like in polar form. And that's what that's what all this is down here. So this is just a repeat of this. That's like the first portion of the picture. Then when we get to pi over 2, that's when we're the farthest out. So we're basically at this point right here. Now, as we go from pi over 2 to pi, and then to 3 pi over 2, we keep going out less and less and less. So that's why these points down here are going out less and less and less. So that. Then when we're down here, actually I'll say this, when our angle is down here at 3 pi over 2, we don't go anywhere. And that's what's happening here. Going out less, less, less. Let me zoom in a little bit. Maybe I can put both right here. There we go. Right, so going out less and less and less, going out less and less until it's right at 0. So this point corresponds to this point on our polar graph. Then once you get past 3 pi over 2, you start going out a little bit more until you end up right here at 1 again at 2 pi. And so that finishes the picture. So altogether, our picture looks like this. This is what's called a cardioid because it looks like a heart. It's also why cardioid microphones are called cardioid microphones for anybody that's into audio engineering and such. Okay, so that's how you graph these things. You're going to get lots of practice with this. I encourage you to practice it a lot, but really it starts by being able to graph the basic trig functions. So you want to be able to graph trig functions comfortably in their Cartesian form, and then you can just look at that graph and read off where to go. You can just read off where to go. All right, so what I want you to do is I want you to try this one. So let me throw up the thinker. Think about how you would start graphing this one. All right, now say something out loud about what you would do to start. What would you try first? All right, now go ahead and try to do it. So start by graphing the Cartesian version of it. Just pretend r is y and pretend theta is x, and graph the basic Cartesian curve, and then use that to graph the polar curve. And we'll do it together in a minute. All right, let's look at it together. I've got this graph nicely on the slides here, but I'm just going to kind of point out where the arrows are. So let me go ahead and pick a green arrow. So one thing I'll point out is that this is the graph that's going to inform how to graph this. So let's look at it. As I go from 0 to pi over 2, my radii behave this way. So getting larger, 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 and then I'll be all the way out at 2 when I'm at pi over 2. So what's happening is this, 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 this. So this distance right here is 2. Notice I'm on the circle of radius 2 at that point. There we go. Now as we keep going to pi, our radii decrease to 0. All right, so what's happening here is going like this, 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 this. And then now when we're pointed out this direction, we're actually not going anywhere. Our radius is 0 when we're facing that way. So we're just going to be right here at that point. Now here's where things get interesting. I'm going to switch the color here. So after pi, so basically when we're facing this way, notice that our radius is negative, right? We're in the negative region here. Our radiuses are negative, but getting larger in size. So what this is saying is that even though we are facing these ways and these directions, in terms of the angle, the radius is negative, so those arrows are going to get reflected back across the origin. So what it's going to look like is this. Even though I'm facing this way, my arrow is going to go this way. And even though I'm facing this way, my arrow is going to go this way. And even though I'm facing this way, my arrow is going to go this way. Facing this way, arrow will actually go that way. And so what you end up doing is you end up getting this circle a second time. You get that whole circle a second time. And that's why this graph just looks like a circle. There we go. Cool stuff, huh? So that's how you can interpret the negative radius. Just takes a little bit of practice. All right. Okay, now you try this one. So here's another one. Go ahead and think about how you would start this one. All right. Now say something out loud to yourself about how you would start. You probably got a pretty good idea now. All right, now try it on your own, and then we'll do it together in just a moment. All right, here we go. So hopefully you remember a little bit about how to graph something like this. Changing this coefficient here of the argument changes the period of the function. And in this case, because that number is 2, it's bigger than 1, so it's going to shrink the period of our function. And our cosine curve is going to make a full rotation, or I'm sorry, it's going to have a full period in pi radians instead of 2 pi radians. So the graph looks like this. The graph looks like this. Let me go back to this, like so. And just like before, let me go back to my green arrows here. Just remember that this Cartesian graph is going to inform how to do this polar graph. So you just got to be able to graph the Cartesian graph first, and then just look at these lengths. So here, this is pi over 4 right here. So as we go from 0 to pi over 4, our radius starts at 1 and goes to 0. So here's the first arrow. Actually, you know what I'm going to do? This. Watch. So this first arrow is this arrow right here. And then this second arrow is this arrow right here. And then this is this. And then you'll see that as we get to pi over 4, our radius goes to 0. And that's why if you look at this little petal of the rose, our arrows keep leading us back to the pole. Right? So that's how that piece starts. Now here's where it gets fun. Let me go to a red pen here. After we pass pi over 4, our radii are negative, and they grow, and then they get smaller again. All right, so what's happening is, as we're facing this way, as we're facing this way, our radius is actually the opposite of that. So even though we're facing this way in terms of an angle, we're actually going to draw this way. And then as this increases to pi over 2, we're going to be instead reflecting and going opposite. So basically, as we're turning this way, we're facing the opposite direction and coming around like that. All right, then we end up circling back to the pole. So here we're at the pole again. So this point is corresponding to this point again. The zeros of this function correspond to being at the pole. That's what's happening there. Let me go back here. There we go. All right, let me erase. Now, back to green. When we're here, our radius is positive again. And so we're going to be circling where? Where are we going here? Oh, right here. Wait, so what is this? To pi. So we're facing pi. Yeah, that's right. So now we're going to be going this way for these arrows. Right? These ones. Then we hit the pole again, and then everything is reversed again. All right, so I won't draw the last set of arrows, but what I am going to do now is I'm going to try to sketch the curve in one fluid motion, and maybe this will kind of hammer the point home. Let me erase all these little arrows. Okay, so in Cartesian form, this curve gets traced out like this. In polar form, this curve gets traced out like this. All right, here I go. Boom. Did you see it? All right, let me try that again. So we started over here, right at this point, and then as this swoops down, this goes around. And then as this swoops down farther, this swoops down farther. And then as this keeps going this way, this keeps going this way. And then as this keeps going this way, and so on, and you end up back to where you started. So that's what's happening. So let me try to do it in one smooth motion one more time. Not too bad. There you go. That's how you graph these polar curves. All right, so now let's take a look at a Desmos example. One thing I'll say is if you would like to basically quit at this point and not finish the rest of the lecture, you're more than welcome to. I'm just going to be going through all of these Desmos examples, and you should play around with them on your own too. So if you want to explore the different curves, you can. I'm going to go into detail about each one and kind of the equations for each one. But if you would like to do that on your own, you can. But let me go ahead and pull up that. I got to move some things a tiny bit. Oh, let me do this. Got some extra stuff. Doesn't need to be open. Okay. And here we go. All right, cool. We're in business. Okay. So I've got a whole bunch of different types of polar curves here that you can explore and play with. Lines we actually saw. So let's look at lines here. The formula is just I chose horizontal lines, sorry. So r sine theta equals some number. Remember, r sine theta is just equal to y, so this is y equals a. If I change a, it changes where the line is located. Same thing for x equals a. So remember, r cosine theta is x. So now if I change a, there we go. I guess I should turn off this one. There we go. So now we have what's it called? Vertical lines. So there's lines. Now let's look at circles. So remember, circles, those are really, really easy to describe. These are really, really easy to describe when you're centered at the origin. So here, r equals a. That's just a circle centered at the pole, or centered at the origin, with radius a. So in this case, our radius is 1.8. I could pull it in. Now our radius is 1. So this is a circle centered at the origin, radius 1. Now, if we want these kinds of circles, uh, if you have an equation that's of this form, r equals 2a sine theta, then it will look like a circle of radius a right here, kind of like tangent to the pole, you could say. So if I change a and I keep a positive, you just get these things. There you go, just more circles. If a is negative, it reflects through the pole. Not surprising, right? Because if a is negative, that means r is negative. And if your r is negative, that means you reflect through the pole. There you go. Now let me make a positive again. Here are the other circles, 2a cosine theta. So cosine, you'll still be tangent to the pole, but now you're going to be on the left or the right. And if the radius is positive, then you're going to be on the right. If the radius is negative, you'll reflect over here, and you'll be on this side. Oop, there we go. Not too bad, right? So those are circles, circles and lines. Now let's look at cardioids. So here are cardioids, and these are the different equations for them. Cardioids are called as such because they're kind of like a heart. They're kind of heart-shaped. Uh, and again, like I mentioned briefly, if you are into audio engineering or if you've worked with like setting up microphones or setting up sound equipment, cardioid microphones are specifically called cardioid microphones because they have this pickup pattern. And what you do is you put the microphone right here at the pole, and this is the region that it can detect with that microphone. So this is one of the reasons why performers like to use these microphones, because the microphone, like the top of it is right here. And so if they're holding it up to their mouth, it'll pick up them, but it won't pick up the audience who would be behind them. It picks up very, very little behind the microphone. Let me zoom in a little bit. Let me change A. I'll do that. Here we go. So yeah, the microphone's here, and the bulb of the microphone would be right here. So the cardioid microphone won't pick up much behind it, but it will pick up a lot in front of it. So if the singer is right here, it's going to pick up the singer perfectly. But if it's back here, it won't pick up the audience. That's the idea. You can take a look at the structure of the equations here. So cosine means you're going to have a horizontal cardioid. Sine means you'll have a vertical one. Uh, just like before, if A is negative, then it switches like so. It switches like that. But cardioids always have a cusp at the pole. That's one thing to keep in mind. So your cardioid will always have a cusp. Unless you shift it around. You can always shift these things around too. If you shift them around, the cusp won't be at the pole. It'll be at that vertex, but it will always have a cusp. Now, take a look at these equations here. See how it's like A times 1 plus cosine theta? You could also read it as A plus A cosine theta. Now let's compare this equation to that of a limaçon. That's French for snail. So limaçons have a little loop. They have a little loop right here. And that little loop and the size of that loop and the orientation of that loop is determined by a second parameter, B, right here. So check this out. Let me make A positive for now. There we go. So B is 2, and the size of B partially or determines partially what the size of this little loop is. That's what's happening there. If A is equal to B, watch what happens. Or maybe I should say if B is equal to A, you get a cardioid. You get a cusp there instead of a little loop. And that's because in this situation, this would be A plus A sine theta, which is the same as this. Here you go. A plus A sine theta for the cardioid. So limaçons are like a generalization of a cardioid, you could say. And the other thing I'll mention here, let me change B, is that to get this little loop, you will have a negative radius. You're going to have a negative radius, and that's, in this case, yeah, you'll have a negative radius. That's where this loop comes from. So if you don't have a negative radius, you won't get this little loop. That's what's happening there. Again, sines will put you above and below. Cosines will put you to the left or to the right. There you go. And you can, again, I encourage you to go and tweak all these things and play around with them. Oh, look what happens when I make A equal to 0. That makes sense. If A is equal to 0, then this term right here is gone. And so you just have B cosine theta, which is going to be a circle. Going to be a circle. All right, limaçons. Now let's look at roses. So the roses are very pretty. Let's see, A is 0 for now. That's why nothing's showing up. So roses have this type of structure. A sine n theta, or A cosine n theta. And we're going to let n vary. So let me give A some size. I'll pick 1. Let's pick 2. Just make it a little nicer. All right, so right now A is 2. So the scaling factor is 2. And right now n is 2. If n is 1, you just get a circle, like one leaf or one petal of the rose. When n is 2, this sine 2 theta gives you a 4-leaved rose or 4-petaled rose. If n is 3, it becomes 3. If n is 4, it becomes 8. If n is 5, it becomes 5. If n is 6, it becomes 12. And maybe you can kind of see the pattern. Again, I encourage you to play around with these things and mess around with them. Look what happens when you let n get really big. There you go. If you're interested, an interesting question is how much area is inside the rose, inside the petals, and how much area is outside the petals? Maybe if you're just looking at the circumcircle, right? So the circle that surrounds this rose. Interesting question. Well, we'll talk a little bit about it in the next section. So that's what the roses are. Cosine, let me back N up a little bit here. Cosine looks like this, and you get a similar behavior, but you'll notice that everything is rotated a little bit. And so let me go back down to like this, n equals 3 for cosine versus sine. So you get a bit of a rotation. That's the difference there. Okay, let me hide that one. Now let's take a look at what are called lemniscates. So these are lemniscates. This one I actually had to break into, oh wait, do I? No, I guess I didn't. Okay, so lemniscates have roughly this structure. But generally they're given not as a function of theta, but they're written as r squared equals something. So like r squared equals a squared sine 2 theta squared. And that's what you get. So kind of just looks like this. They're basically infinity signs. They're the infinity symbol, but rotated at an angle. That's what a lemniscate is. It's an infinity symbol. There's that one. There's this one. In this case, we're getting the same equation because r squared gives you plus or minus, right? Here's the cosine version. The cosine version really is the infinity sign. So this is the infinity sign right there. There you go. So if you want to get like an infinity sign tattoo, but you didn't want to just do a basic infinity sign, you could be extra cool and get r squared equals a cosine 2 theta squared, or a squared cosine 2 theta squared. Get that tattooed on your, or no, just a cosine 2 theta. Don't get the wrong formula tattooed. Don't get the wrong formula tattooed. Um, so consult with a mathematician before you get that tattoo. But if you wanted to, there you go. There's an equation for the infinity sign for you. Okay, and now the last one is spirals. So we're going to look at two different kinds of spirals. And in polar coordinates, spirals are very easy to describe. All right, so let me do the first one here. Okay, so a spiral of this form is what's called an arithmetic spiral, because it basically looks like a line. Not the picture, but the formula looks like a line. It's like y equals mx plus b. It's got an arithmetic structure. Um, but it's still in polar form. So theta is an angle and r is a radius. And again, there's two parameters. There's a and then there's b. So I'm going to vary those now. Here's what a does. So a basically kind of pushes you away from the pole. You can't really see much of it. There we go. Let me zoom out. There's the spiral for you. So a kind of pushes you out. If a is negative, you get this behavior here. You start to get a tiny little loop at the beginning. There you go. That's what it looks like. B changes the tightness. So if you change the tightness, remember this is basically saying how almost like how quickly the angle passes through, right? So if I increase B, whoa, there we go. It spreads everything out. If I make B very tiny, it starts to pull everything in. There we go. So that's an arithmetic spiral. One thing you can see is that these distances are all equal. This is one of the reasons it's called arithmetic, because there's like an arithmetic progression as you go through the loops, and they're all the same distance apart. That's basically what it is. Now compare this to this version of a spiral. This is a logarithmic spiral. So let me pull this one up. This is a logarithmic spiral. Let me change things a little bit here. Let's bring B a little bit smaller. There we go. There you go, change A a tiny bit. So this logarithmic spiral, what you can see is that the loops are getting farther and farther apart as the angle increases, right? Maybe you can kind of see it. There we go. There we go, yeah. So as B gets bigger, it pushes the spiral farther apart. But this is what you see when you see things like like a shell on the beach or something like that. They grow in a logarithmic spiral as opposed to an arithmetic spiral, which would look like this. Oop, a tight arithmetic spiral. There you go. That versus that. Different kinds of spirals. All right. Okay, now we go back to this. Okay, so that's it for the Desmos demonstration. I hope you enjoyed that. And on that note, let's play. So that's the end of this lecture. Again, I know, thank you for bearing with it. I know sometimes these can be a little bit long. I won't drone on for too long, but again, I encourage you to play around with that Desmos example and just to practice getting comfortable with these types of curves. You will have to graph these kinds of curves a lot in the future, so practice it now while we have some dedicated time to do it. And then next time we're actually going to see how to do calculus with this new coordinate system. All right. So until then, thank you again, and I'll see you next time.